this video, vector space homomorphisms are discussed. First, we have the formal definition of a homomorphism. Let V and W be any two vector spaces over a field F. Then a mapping T from V to W is called homomorphism if U plus V of T is UT plus VT and alpha UT is alpha into UT, where alpha belongs to F and U and V are members of capital V. A homomorphism T of a vector space V is also called a linear transformation on V. That is, in the case of a linear transformation, we have T to be a mapping from a vector space V to itself. Now we also have few definitions, namely isomorphism, epimorphism. Then when do we say the two vector spaces are isomorphic to each other? So if we consider T from V to W to be a homomorphism, then T is called an isomorphism if T is 1:1. So 1:1 homomorphism from a vector space V to W is called an isomorphism. And then T is called an epimorphism if T from V to W is onto an homomorphism. V is said to be isomorphic to W if there is a mapping T from V to W which is 1:1 and onto. A linear transformation T from V to F. We know that F is also a vector space over a field F. So that is over itself and over its subfield also. So we can consider F to be a vector space over itself. So that T from V to F, where V is a vector space over F, then T from V to F is called a linear functional. Now these are few examples. If we consider T from V to W defined by Vt is equal to 0, that is, T is the mapping which takes all the elements of V to just the vector 0. So it is actually T is a 0 transformation, a 0 mapping, and that will be a homomorphism. The conditions can be easily checked. So it is called a trivial homomorphism. And then identity mapping from V to V is defined in this way, that is, it takes any element to itself. Then this is also a linear transformation, that's called identity linear transformation. And another example, T from R2 to R2, that's defined by any element in R2 is an ordered pair. So T takes that element to, say, the ordered pair 2A minus 3B and A plus 4B, that's in the second component. Then it can be easily checked that this T is a linear transformation for the reason that U, if we take U as ordered pair AB and V as ordered pair CD and alpha to be a member of R, then U plus V of T, we are replacing U by ordered pair AB and V by ordered pair CD. So by component wise addition, that we get A plus C, B plus D as the first and second component. And then by the definition of T, we have this to be 2 times A plus C minus 3 times B plus D, and the second component A plus C plus 4 times B plus D. Then we rearrange the terms, and then again we can split and write like this. So this one gives the image of AB, ordered pair AB and a T, and this one gives the image of CD and a T. So when we consider alpha UT, then it is alpha into ordered pair AB T. By the definition of component wise scalar multiplication in R2, we have this step, and by the definition of T, we have this step. And in this we can take that alpha out so that we get this, and this is nothing but alpha into the image of ordered pair AB and a T, and that is alpha into UT. So we have T to be a linear transformation. Next we have the definition of kernel of T. If V is a vector space over a field F and W is another vector space over the same field F, and T is a homomorphism between them, and if we have 0 mapped onto the 0 element of the codomain, and which is the identity element in W, and if V is another element which is also mapped down to 0, V prime is another element of V which is mapped down to 0, and V double prime which is another element which is mapped down to 0, and so on, then the collection of these elements is called the kernel of T. In the case of trivial homomorphism, it can be easily seen that kernel T is capital V. That is the entire domain that we get as kernel T. And in the case of identity linear transformation, we can see that kernel T is singleton 0. And suppose we have T from R2 to R2 defined in this way. Any ordered pair AB is taken to A minus B, ordered pair A minus B, A minus B. Then kernel T we can easily see to be the set of all vectors which are ordered pairs with entries AA in the first and second component. Actually, it's aligned through the origin. Now, these are the properties which will be used whenever we have a vector space homomorphism. Let V and W be vector spaces over a field F and T from V to W be a homomorphism. Then T takes identity element to identity element, and the image of the inverse of an element under T is the inverse of the image of A under T. So if we consider the first one 0T, we can write 0 as 0 plus 0. So 0T is 0 plus 0T is 0T plus 0T, and T is because T is a homomorphism, we have this step, and because of this we have 0T to be the additive identity of W. That proves the first part. And then for the second one, we start with the first 0T equal to 0, and that is written as A plus of minus A for any A in V. So because T is a homomorphism, we have this step, and AT plus something gives me 0, which means this should be the additive inverse, and that is how we have this step. So next we have the result. If V and W are vector spaces over a field F and T from V to W is a homomorphism, then Vt is a subspace of W. To prove this result, first we consider Vt, which is the collection of all elements of the form, the image of V and a T where V range over capital V. Now because T is a homomorphism, it takes the identity element to identity element, therefore 0 can be written as the image of 0 and a T, and it's an obvious member of Vt, and therefore Vt is a non-empty subset of W. Next we consider W1 and W2 to be any two members in Vt and alpha beta in F. Then there exists V1, V2 in V such that W1 can be written as V1t and W2 is V2t. Now we consider alpha W1 plus beta W2. That is nothing but alpha into V1t plus beta into V2t. Because T is a homomorphism, this is the image of alpha V1 and T plus image of beta V2 and T. So again, because T is a homomorphism, this is rewritten as the image of alpha V1 plus beta V2 and a T. So this implies that alpha W1 plus beta W2 belongs to Vt, and hence Vt is a subspace of W. Next result is if V and W are vector spaces over a field F and T from V to W is a homomorphism, then kernel T is a subspace of V. So again, to prove this, we consider kernel T, which is all those elements of V which are mapped down to the additive identity of the codomain. Now since T is a homomorphism, it takes the 0 element to 0 element. So you have 0T to be 0, and therefore 0 is a member of kernel T, and therefore kernel T is a non-empty subset of V. Now let W1 and W2 belong to kernel T and alpha beta to be in F. Then W1, the image of W1 and T is 0. Similarly, the image of W2 and T is 0. Now you consider the image of alpha W1 plus beta W2 and T. So that is because T is a homomorphism as alpha into W1T plus beta into W2T. So that gives us alpha into 0 plus beta into 0, which is 0, and therefore alpha W1 plus beta W2 belongs to kernel T, which shows that kernel T is a subspace of V. Then we have this result that if T from V to W is a homomorphism, then T is an isomorphism, that is T is 1 to 1. Because already T is assumed to be homomorphism, T is 1 to 1 if and only if kernel T is singleton 0. So to prove this, first we assume that T from V to W to be an isomorphism, that is T is 1 to 1 and homomorphism. Now to prove that kernel T is singleton 0, we consider small v to be any arbitrary element in kernel T. Now because V belongs to kernel T, Vt is 0, and because T is a homomorphism, that 0 can be written as the image of 0 and a T, and because T is 1 to 1, we have V to be 0. Images equal implies the pre-images are equal, so that's because T is 1 to 1. So V being an arbitrary element in kernel T should be just singleton 0. Now for the converse part, we shall assume that kernel T is singleton 0, and to prove that T is 1 to 1, we'll assume that Vt is equal to V prime T. Then we have this step, and because T is a homomorphism, we have this step. And by the definition of kernel T, this is V minus V prime is a member of kernel T, and kernel T being singleton 0, this implies that V minus V prime is just 0, and that in turn implies that V is equal to V prime. So images equal implies the pre-images are equal, and therefore T is 1 to 1.